Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I have Rodrigo de Salvo Braz here from UC Berkeley, where he's doing a postdoc with Stuart Russell's team. I'm very excited about this topic area. For quite a few years, the uncertainty in AI community has focused on largely propositional representations, Bayesian networks, and all this various diagnostic reasoning. Predictive modeling typically assumes you have a fixed set of propositions. And one of the directions that's kind of exciting is in opening up our systems to the open, to have more of an open world intelligence, is to mesh first order inferences with the probabilistic calculus, and there's been a kind of explosion of representations. I wouldn't call it an explosion; I call it a mini firework of representations that combine first order logic with probabilistic inference. Rodrigo did his master's and bachelor's degrees at the Universidad de Sao Paulo, and after that he got fascinated by intelligence and went off to Brown University for a couple of years in the cognitive science department, doing work in neural nets and in descriptive models of various kinds, and as we discussed last night at dinner, got a little frustrated with that work and went off to pursue his PhD more centrally in inferential methodologies, core AI, and this was at the University of Illinois, Champaign-Urbana, working with Ayel Amir and Dan Roth and others there. He's been a postdoc in computer science at UC Berkeley, and just recently informed me that he's probably going to be taking a position at SRI pretty soon to continue this work as an adult, a full-time researcher there. So Rodrigo on first-order probabilistic inference.
Well, thanks for the introduction and for having me over. It's very exciting to be here. I have always wanted to visit Microsoft Research. It's nice to finally make it. So today I'm going to talk about my work in my PhD and also in the postdoc. It's actually two different parts of the same subject. In my PhD, I worked with what we call the lifted first-order probabilistic inference, meaning inference that's performed not only on a first-order representation, but the inference itself is also kept at the first-order level, as opposed to having a first-order representation, generating the propositions, and then doing the inference at the propositional level. So that was my PhD thesis. Then I went on to work with Stuart Russell. He was also working in first-order probabilistic inference, but from quite a different point of view. He was working with a language that was more expressive, more complex. He was working with open universe assumption. But his inference was still propositional. He was working with sampling, whereas I was working with simpler languages and more sophisticated inference because it was first order. But then because of that, I couldn't deal with as much expressivity as he did. I didn't have the open universe assumption. So it was a nice compliment to work with him on that, and that's what I have been working on in the past year in his language that he calls BLOG for Bayesian Logic. So I'm going to talk about those two topics, and hopefully one day they will integrate nicely, and we're going to have all these things in one.
That's the mini firework.
Yeah, so that's it. So just ask any questions, fireworks if you like, for questions, because sometimes I find that some of this topic may look ambiguous to some people. It's good to clarify things right away. If you want to follow, I'm surprised people don't have laptops here. Usually everybody's like with their laptop. Amazing.
I'll turn it on.
There you go. So for those that have laptops, they can follow the slides from our webpage. All right, so these are the parts of the talk. First, I'm going to talk about first-order probabilistic inference in general, the goal that it represents, what kind of things we want to achieve in the future with that. Then I'm going to talk about my PhD thesis, lifted inference, then DBLOG, which is an extension to blog that I have been working on, and the conclusions. So the thing I'm mostly interested in is to abstract inference and learning from different AI problems, right? We are all working on different problems in AI, and even though we share so many techniques, so many ideas about inference and about probabilities and so on, still, often it is the case that we have separate solutions that are tailored to our problems. And of course, that makes it harder to reuse those solutions to new problems that come along, and it's also harder to integrate problems. If you're working on a problem, I'm working on another one, to integrate those two solutions, it may be quite a piece of work, and we have to rethink our models because of that. So it would be nice to abstract all these problems and solutions by separating the knowledge and the inference and learning mechanisms that we are using. And once we do that, hopefully we can do this. We can have just one box that does the inference and learning for us, so we can just put in the knowledge about specific problems and use that. That's a vision that AI has had since the beginning of AI, I suppose, but it's still something that's not quite realized. So if we want this magic box that does inference and learning, what should it do for us? One thing that everybody seems to find very useful, especially if you're describing more complex problems, is to have predicates or relations and quantifications over objects. This is something that's very powerful. You can describe many different problems using this. So at first, people did that with logic. But then we also want other things. For example, we'd like to have knowledge that has varying degrees of uncertainty, because often that's the case in problems, that we have knowledge, but that's not a certain knowledge. Here, I'm not committing to any specific uncertainty representation. So I'm just using these brackets, these red brackets around my sentence to say, this is uncertain in some way that I may commit to some form later. But just to say, it may be that I have a tank. Usually that means the color of the tank is green, but not necessarily. So those two things are pretty important in different problems, different domains like language and vision and many others. And eventually, even though that's not something I'm concerning myself with right now, but you also want this box to be able to use other things like modal knowledge and utilities and things like that. But for now, we're concentrating on the predicates and not probabilities right now, uncertainty. So I was talking about integrating problems, right? So if I have domain knowledge about some common sense reasoning task, I'm thinking about a military situation with tanks and planes and the colors of objects and so on. I have that knowledge there. And I also may have, even related to the same domain, something involving natural language processing. And I have also knowledge involving that, about how verbs interact with the meaning, what does it mean to use the verb attack, and so on. And if we share this inference and learning module, then it should make it easier for us to actually integrate those things. And what's the point of integrating that? The point is that you have a lot of synergy, a lot of feedback between those two pieces of inference, of knowledge going on. You can resolve language ambiguities by using common sense reasoning facts that you are also observing. So bringing everything together may help you with all of the problems at once. You can use the language for the common sense and vice versa. I think that when humans solve problems, they use that a lot, and I think that's a major direction for AI, to integrate things as much as possible. And that's why I'm so interested in, a very general language that can do that. So I was talking about predicates and things like that, and uncertainty. Logic has those objects and properties, a very rich language, but then for standard logics, the statements are usually absolute. So that doesn't do what we're trying here. And graphical models, which are and machine learning techniques, they have They involve lots of uncertainty, but then usually, as Eric was saying, you assume a fixed set of propositions, and if you have objects that parameterize different propositions, it's not so easy to use that with those models. You usually have to have a separate thing, separate module that generates new instances of problems for you, and it's a separate different stage. And usually that's even manual solution, so that's not so convenient. So just to give you a flavor of what you may do with graphical models if you need to use objects and knowledge that is quantified. If you have that piece of knowledge there, so you're saying that an object is either a tank or a plane, and if an object is a tank, usually the color is green and so on. And if an object's next to each other to a tank, then probably it's also a tank. So if you want to use that kind of thing and you have the evidence that the color of a certain object is red, the other is green, you can create a graphical model that represents that. It's important to notice that even though I'm naming these variables with this not so usual notation, parameterizing with parentheses here, from the point of view of a graphical model inference algorithm, those are just strings. They don't know the structure that's involved in this problem. They don't know that this is the same type of variable as that, and that the same type of knowledge applies to both of them. So the algorithm cannot take advantage of that structure. Also, you have to do this transformation, right? And that's not something that the framework of graphical models necessarily brings to you. That's something that you have to come up with a solution for yourself. And as I said, the algorithm doesn't know that this is talking about objects. For the model, for the algorithm, this is just a bunch of random variables. And another interesting thing is that if I have a different evidence, I still have the same model, I still have the same problem, the same solution. I would like to have one model that can be used with different evidence. But here, every time I get new evidence, I get a different graphical model. So formally, technically speaking, I got a new model, a different model that formally is unrelated to the first one. And it would be nice to be able to formally establish how they relate to each other and that they in fact are representing the same knowledge and the same things. So we also lose that kind of thing if we do something like this. So what I just showed you is a technique called propositionalization, which is just generating the random variables from first order representations. So a lot of people worked on something like that, right? They came up with languages that were very expressive, and when they actually had to do inference, usually they will create a graphical model with the disadvantages that I mentioned before, right? And these languages, they have all different sorts of flavors. Some of them look like graphical models, some of them look like logic, some of them look like databases, some like description logics. Actually, I think the field took quite a while to understand that these things were doing essentially the same thing. It wasn't so clear at first. It wasn't so clear what the semantics of a probabilistic relational model should have. So that's why I think we got so many different models. And eventually people started realizing we're really just talking about predicates, and each ground literal atom is going to be a random variable and so on. So you also have from Hackerman, Meek, and Kohler. From MSR, you have the system Daper. It's one of the systems in this line. So what people use is what I would call smart propositionalization, because they don't generate all the propositions. They don't just dump a set of propositions and generate a graphical model. They try to do something smarter than that. They only instantiate those variables that are relevant to the evidence and the query at hand. And so you can actually create something that's a lot smaller than you would just by propositionalizing. So that's usually the flavor of what people do. Just to give you an idea about this type of model, one of them, which I find pretty typical, is Bayesian Logic programs, which by the head and Christian Kirsten. So they designed the language to look like Prolog, but instead of using the usual Prolog implication symbol, they used the conditional probability symbol. Because these are like Prolog rules, but they actually have associated CPTs and also combination rules in case you have two different rules that are parents to the same variable. You need to somehow combine those two different CPTs into one. So if you are given this bunch of rules like that, then you have something that will generate graphical models for you. So that's more or less how it works. If you have to decide whether a battalion needs rescue in some kind of situation, and that depends on whether there is a soldier in that battalion that's wounded. So if you have a wounded soldier, you need a rescue operation there. And the way it will work is by applying Prolog inference and building a proof tree and using that to build a graphical model like that. So by doing that, you actually concentrate on the random variables that are actually relevant to your problem. You don't propositionalize everything. But still, you go and instantiate, in the case of a battalion, you're going to instantiate variables for all the soldiers that you have in that battalion. This generation of graphical model happens even before you actually start doing the probabilistic inference. So say if you determine that a soldier is wounded, that doesn't help you preventing the instantiation of other variables, because you could in principle think of that, right? I already know this guy is wounded, I already know I need rescue, but because we're generating the graphical model before even considering things like that, it's going to generate the graphical model first, and then it's going to do the probabilistic inference. On the other end of the spectrum, something that it's a first order model that looks like graphical models. It's work done by Lasky called multi-entity Bayesian networks. It's essentially a bunch of templates. Each of them look like a fragment of a Bayesian network, but then the random variables have these parameters. And in this case, the model does know that those are parameterized random variables and uses them to instantiate new fragments. So if you give evidence, you give a certain situation, it uses those objects to plug into these variables here. Then you have a bunch of fragments that have to be combined into a new, to a regular Bayesian network, and then it does the inference. So you just instantiate the fragments and you put everything together. So here you have two fragments of the same variable, you somehow combine. And not surprisingly, you get something very similar to what the Bayesian Logic programs do. You get a similar graphical model here, even though the representation looks pretty different. Okay, so that's kind of work people have been doing until pretty recently. In my PhD thesis, I did this lifted inference approach, which I'm going to explain now. Any questions so far? Just to clear that up. All right. So, lifted inference. Suppose that I have that same query. I want to know if a certain battalion needs rescue, right? Instead of instantiating random variables for each of the soldiers, like we were doing before with those other approaches, I could do something that looks more like logic inference, in which I determine the kind of things that will be relevant to my query. But instead of instantiating everything, I leave them instantiated. I just say, well, I just need that kind of that class of random variables to answer this query. I'm showing this is not a formal explanation. I'm just giving the idea about how you can go solving this problem without having to actually instantiate everything. It's the way that maybe most people would think about solving it if they had to do it by hand. We wouldn't start thinking about each individual soldier if we had to decide that kind of thing. We would think, well, a battalion has a bunch of soldiers. I have to check whether the soldier is in the battalion, is wounded. So how do I do that? If I have another rule that a soldier can be wounded depending on whether the battalion has been attacked, then I can decide, I can check if the battalion has been attacked and think about that. Well, the battalion has been attacked, so I have so many soldiers. Each of them has a chance of having been wounded. So what's the probability that I do get at least one wounded soldier? So I think that's how most people would do that by hand. They wouldn't go over instantiating everything. And it's a faster approach. You don't have to instantiate. It's more compact. It's also more intuitive. And it keeps the structure of the problem, right? Because during inference, I know that this represents a class of random variables, and I know that they are all related to each other, that they all have the same knowledge on them. And I have that information available for my algorithm. I can use that to make better decisions. So that's the gist of lifted inference, just keeping things uninstantiated as much as possible. This is just a very quick review of Bayesian nets. I think you guys are up to date on that. So,
I have a question about
yeah,
the previous.
sure.
So you have sort of the, I don't know what to call it, the any concept. Like if any soldier has been wounded, then that variable is true. And then you mentioned having to do this inference that an attack causes a probability of wounding of one particular soldier, and if you have n soldiers, you know, what's the probability that no soldier is wounded? That's a complicated thing. How many of those sort of complicated atomic things does this have to be able to do?
Why do you say it's complicated? You have an independent probability of each soldier being wounded, right?
Right. In and of itself, it's not complicated. In and of itself, it's, you know, that's a procedure that you can follow to see that if you have some probability of something happening to any member of a collection, you know, then what's the probability that it hasn't happened to any at all, or that it's happened to one of them? Is there any other type of
I see what you mean.
inference that
You're talking about? This is almost like an inference step,
right.
A way of doing inference. Yeah,
It's
almost like an inference rule.
Right. Are there other inference steps?
Yeah, that's a good point. This is the main one. That's the one that's the essence of it, I would say. But
each thing in a collection has a probability by itself, and then
but that doesn't work for all situations, right? Because you may have situations in which things are not as independent. And then I'm going to talk about that. There is another way of doing it, which I don't show right now, but takes into account the dependencies between things. So yeah, you can think of it as inference rules, and you may have some of them available. We have two different ones, and we have a third one that kind of links the first two together. It maps one situation well, after I talk about the actual operations, then I'll mention this third one. Okay, so Bayesian networks, you have a joint probability that's a product of conditional probabilities. You can also use factor networks, which is a notation that I use more often, so I'm showing it here. This is essentially the same thing. You have a joint probability that's proportional to the product of these functions. You can represent that Bayesian net using factor networks if you want. Then you have the task of marginalization. You're just summing out a bunch of variables. You can do that with variable elimination. You can efficiently factor functions out and start obtaining new factors. Here I'm using the color green to show new factors obtained by summing others out. So you do that, and you eventually get a function that's only on your variable of interest, and that gives you a marginal probability. So I was just showing that to kind of introduce graphical notation that I was using and so on. So if I have a factor network with lots of redundancy like that, I have, again, here the parentheses only have meaning for us, not for the model. I have several diseases, and I may have epidemics of those diseases going on, and I may have people who are sick with those different diseases, and people may be hospitalized or not. So whether Bob is hospitalized or not depends on the various diseases he may have and so on, and whether people are sick depends on whether there are epidemics and so on. And I'm assuming here, and that's a very naive model, that this function is exactly the same as that, so that if there is an epidemic of flu, the probability of someone getting that disease is exactly the same as if there is an epidemic of measles, someone getting that disease, getting measles, which It's a naive thing, but will do for illustrative purposes now. So if I have a model with lots of redundancy like that, I would rather represent it in a more intuitive way. I'm just talking about different diseases and people getting sick and being hospitalized, so I could just say, well, those are the relations that I have in my model. And I have this slide just has the point of showing and defining terms. So I could call those classes of random variables atoms just because they are pretty much the same thing that you have in logic. And you have the logical variables, which are the parameters to these atoms. Those factors that actually represent many different instances of the same function, we call par factors for parameterized factors. And we can also constrain their instantiations. I can say, well, that factor holds between instances of those two classes for the cases in which P is different from John. So for John, that doesn't apply. So that's the kind of representation that I'm using for lifted inference.
Because you could make like that potential, you could say.
You mean I could represent that constraint as another factor? Is that what you're
Right,
saying?
as a parameterized factor.
I could do that. We keep them separate because those are deterministic factors. They have their own different behavior, and it's more convenient for computational purpose to keep them as constraints. It's going to be hopefully more clear when I show it. So what's the semantics of such a model, right? So if I give you this first order model, what's the semantics of it? It stands for exactly the same thing as if I propositionalized everything. It stands for its full instantiation. That doesn't mean I'm actually going to do it. It just means that's what it's representing. That's the joint distribution it represents. And each factor here is just going to be the instantiation of the par factor with particular objects. If I do that, I have a standard graphical model and I have a joint distribution. So let's see the operations that we can do with more detail, right? So the first one, which is the one we were talking before, is the inversion elimination. And inversion elimination works the following way. In just one step, I can sum one of the classes out, just like that. It's very much like variable elimination, but of course it's not variable elimination because here I'm talking about classes of random variables. I'm talking about when I sum over this, it means I'm treating this atom as if it were an individual random variable, even though it's not. That's how the operation works. And of course, to do such a thing, you have to justify that it's correct, that you can treat an atom as an individual random variable, and that's still valid, right? But that's what it does. So you just sum it out, you get a new function that's on the remaining classes, the remaining atoms, and you have a new first-order representation that represents the marginalization over the instances, all the instances of seq PD. Yeah?
So here, so far you have not shown condition probability tables between any of your standard models which start bothering because you start doing some action. So if I understand that correctly, for a specific P, if I have probability of epidemic, I have probability of sick given epidemic, and I sum over the sick and I get the probability of epidemic.
Yeah.
And if it's the same for all P's, then of course I can do it for an arbitrary P. Is that what you're assuming? For every person, the relationship between sickness and epidemic is the same.
Yeah.
And therefore you do it once on an instantiation.
Yeah. That's right, but it doesn't work all the time. Because here these variables, they don't interact with each other. The instances of seq PD, they are not interacting directly with each other. If they did, then if you work out the math, you'll see that you cannot do that. If you do that, it's just going to be incorrect.
are you pushing to a direction which you look on the high level, on the first order representation, and you do something there that is more efficient in some ways than going down to the proposition and doing it? Or
Yeah. Actually, the rest of this slide is this, right? So the idea is that I could instantiate everything, do variable elimination over all the instances, obtain these guys here that are just over epidemic random variables, and now these instances can be represented by that. Instead, I'm just doing it directly on the first order level. I never go down the propositional level. You can think about resolution, right, in logic reasoning. If you have first order resolution, you can look at it from that point of view. You're doing resolution over quantified clauses. And it is just as if you had instantiated all the clauses, done resolution in each of them, and then going back to first order level. So this is the same idea. Yeah.
So I'm still a little confused. So you're still summing over all sick, like all people times disease number of sick predicates, right? The sum that you showed is still a sum over all, like number of people times number of diseases.
No, the sum is just over one symbol. I pretend that's an actual random variable. Let me get that. What I do, so this is a binary variable, right? So I'm just going to say, suppose this is false. I plug it here.
I mean, it's false for all people and all diseases, or for a given person and disease.
You can think of it for any person. I'm going to do a summation for, because these things are completely separate, right? They are like this, have this parallel structure. I can pretend that I'm doing the summation just for this guy. Once I do it for this guy, this is going to be exactly the same, because the potential doesn't actually depend on the objects. It only depends on whether this is true or false. So if I do the summation for here, I obtain a new function that depends on that, and that's going to be exactly the same function I'm going to get for this one. Because all these sub-problems, they all have exactly the same structure. And the actual numbers don't depend at all on the objects.
So the number depends on the true or falseness of the predicate.
Yeah.
So the sum needs to know, I mean, you're going to end up with true terms and false terms. So, I mean, you just need to know the number of true and number of false, and that's how you do the sum. I mean, you can move on if you want.
No, that's okay. You're asking if I need to know the number of objects that are true and the numbers that are false?
It's going to depend on that, right? So.
Yes, but because you have this nice structure here, and it's not something that's general, it's only in some situation like this one, you can actually ignore that fact. Because they're all independent, so you can, it's as if you're factoring things out. Suppose that you do decide to do it on the propositional level. You're going to have your summation, it's going to be a summation over all these random variables, right? All of them. You're going to have many of them. And you also instantiate all the factors. Because they're all independent, you can factor each instance of a factor to its corresponding summation. And you're going to end up with a summation over one factor here times a summation over another factor here. And they're all going to have exactly the same structure because they don't depend on the object. So you do the first one or whatever, and you know the result for all of them. And then you get these guys, a bunch of instances of factors that all look the same. And because they all look the same, you can just abstract back like that. I'm going to move on because otherwise it's going to take a lot of time. But we can talk more about it. If you want. Are you on my schedule, by the way? Yeah. Okay, good. So inversion elimination. This is actually something that was proposed by David Poole in 2003. And he didn't actually formalize it very completely. And the way he presented it was as if it would work every time. Basically, he was saying what you were saying more or less. That, oh, I'm just using generic objects. It applies to all the objects. But actually, that doesn't work all the time because if the random variables interact, then you don't have that nice separation anymore. So what we did in the first paper on this subject was formalize it more carefully, and then we realized, okay, that doesn't work all the time. What are the situations that it is correct? and what are the ones that it's not correct. So here's the limitation, right? So because I have all these separate structures that have exactly the same structure, I can do an operation on one of them, and I'm going to get exactly the same result. So it works. But if I have something like this, right? Suppose I say, well, what's the relation between the variables for epidemics of two different diseases depending on the month? So I have that factor, right, that relationship. I cannot just go, suppose I want to marginalize over epidemic. I cannot just apply inversion elimination and obtain something like that and I'm done. That's not going to work. I'm going to get something, but it's just not going to be the correct thing. And the reason for that is that if you ground something like that, you obtain this. You obtain a very connected graphical model. And things are not separate anymore. So when you're summing over one of the variables, that's going to influence the summation of the other one. So it's not true anymore that the summation of over one variable is going to give you exactly what the other would give. So that's the limitation here, inversion elimination. And because of this limitation, we started thinking of other ways of solving things. So for this problem, even though I have all this interaction between these random variables, this is still a very simple thing in a way, because these are all symmetric variables. They all have the same structure, they all have the same knowledge on them. So it seems unnecessary to treat each of them individually, because it's really just a mass of symmetric variables. So can we take advantage of that symmetry? So as we were talking about before, we need to consider joint assignments of that. And that's going to be an exponential number of them. But because they are symmetric variables, an assignment, when I say, well, this is true, this is false, and so on, it doesn't really matter which ones are true, which ones are false. It only matters how many are true, how many are false. So if instead of iterating over all assignments, I just iterate over the histograms, the number of truths and false that I have in that cluster of variables, that's going to be enough. And that's going to be a polynomial number of assignments instead of an exponential one. So that's the other operation that we were talking about, two different operations, and that's another one, counting elimination. And that's a more expensive operation, because even though you have this polynomial number of assignments, it's a number of assignments that does depend on the number of objects that you have. I didn't mention that before, but inversion elimination actually doesn't depend at all on the number of objects. You may have 1 million objects, doesn't matter, because you're going to do the summation for this generic object, and you're going to do it only once.
Bayesian network, or one specific, is months that makes the two epidemic independent, or not? Is it a chain, or they're all related?
Well, this is an undirected graphical model, right? So
okay, undirected, where it's a click between the three?
Yeah. So this notation that I'm using is just like a Markov network, only I'm actually explicitly representing the functions over the... So this is one click. Well, I'm not linking this guy here, but this guy is linking to each of those functions, right? This is a proposition. So it links to all of those instances. Yeah, now I'm kind of regretting not having put the equations here. I think you guys would have appreciated that more. But I can go over that with you if you like. I just wanted to keep it more high level, not get down the details. But the idea is that you're going to have a summation again, but instead of being a summation over generic random variable, you're going to have a summation over the number of values that you have in this cluster. And then you're going to get a potential just on the remaining variable, month. So basically for each month it's going to have a different potential. Yeah?
So this is assuming you don't have any evidence that distinguish between like flu or measles or rubella. So what if you have evidence?
Yeah, that's a good question. That's actually a crucial point, because this all depends so much on things being indistinguishable and symmetric. And if you have knowledge about specific objects, then you actually have to separate those cases. And you do that in the following way. If I tell you, I know for a fact that there is an epidemic of the flu going on. So what you do, you come here, and that's why I was keeping the constraints separate, because they come really handy when that happens. Because then I'm going to break this par factor into different parts. A par factor is just a set of instantiations, right? I'm going to separate the instantiations involving the flu and the instantiations that don't involve the flu. And the ones that don't involve the flu, it's what we call the residual. It's going to be like this. The one different from the two, but also different from the flu. And the other is going to already be instantiated. One of them is going to have the flu. So you separate that. And then once you do that, then again, every par factor involves things that are completely undistinguishable and symmetric. So you go on with your calculations. But in the presence of evidence, you have to do this. It's what we call shattering. Actually, it's even more than, it doesn't even depend only on evidence. If your knowledge distinguishes things in some way, if I have some special rule for the flu, then I have to do that as well. I have to combine that with this rule and separate them. Actually, this is an interesting thing because in terms of logic, because it starts looking a lot like resolution and unification, because when you have to identify the intersection between two par factors, it looks very much just like a unification and breaking clauses like we do in logic. So it's an interesting link to think about logic inference and this type of inference. It starts looking like that. And actually, that's a major limitation of the approach right now, because if you have a database, right, with facts about each of your objects, then this is not going to be helpful to you at all, because you're going to have to look at that database and take all those facts into account and basically propositionalize. You're going to have things for each object. So it wouldn't be helpful in that case. So that's still a major limitation. It's not a limitation that's that you cannot get around it, because you can do something like, I'm going to talk about that later, but essentially you can do some kind of approximate inference that when objects are still not the same, but they have similar properties in similar situations, then you can still consider them as part of the same class. So there is a generalization that takes this approximation into account. But right now, because this is exact inference, we're not doing that. Any other questions before I move on? So this is lifted inference. If you run experiments on this, very predictably you get graphs like that, right? And these operations don't depend. The first one, inversion elimination, doesn't depend on the domain size at all. So if you propositionalize and you do inference, it's going to be an exponential curve, and the lifted inference remains the same. And here, even though the count elimination does depend on the domain size, it's really hard to get a graph that shows that, because the propositionalization of it still grows a lot faster. So for this case in which you have clusters of symmetric variables, those are much faster operations than propositionalizing. All right, so I'm going to move on to the second part of the talk, which is about blog and DBLOG. So have 15 minutes, right? So it's not much. Long, all right. So let me tell you a little bit about blog, Bayesian Logic, which is the work that Brian Milch and Stuart Russell have worked on during Brian's PhD thesis. So it's a probabilistic logic language, just like those others I presented. And its inference is just propositional sampling. You propositionalize variables as you go and you sample them. And what distinguishes blog from other approaches is those two things. It's an open universe language, so it doesn't assume you know the number of objects in the world. You have distributions on the number of objects in the world, which is it's a nice feature and very realistic, because usually we don't know how many objects are out there. And it's also a very expressive language. It looks very much like a programming language. You can write very arbitrary things in it. So here's an example of a blog program. So you declare types. So I say I have this type battalion, and the number of battalions is a uniform distribution. I have this property of battalions. That's a Boolean property. That's just going to be a Bernoulli distribution there, whether a battalion is large or not. You can have the region of a battalion. It's going to be a natural number, and that's a distribution over from 0 to 3. And then you have another type of object, soldiers. And the number of soldiers, it's a parameterized variable. It depends on the battalion. So for each battalion, you're going to have a different set of soldiers. That's going to be it's going to have a distribution too. And you can write that the number of soldiers of a battalion is going to depend on whether the battalion is large or the region of the battalion. And then you can place queries like what's the average number of soldiers per battalion, for example. So because I have distributions on the number of objects, that's an open universe assumption, and also it's a pretty expressive language. I didn't really show, when I was talking about perfectors, I didn't want to be going down to details of syntax and so on, but usually those perfectors, they are just tables, right? So it's a much simpler representation as opposed to here, in which you actually describe the computation of the distribution much more carefully. And you have a lot of structure available there. So it's a more expressive language. You're also talking about sets of objects. You're talking a variable that, average, that's going to be over a set of objects. It's a much more expressive language. So, inferencing blog. So just going back to that first example that I was using of a soldier being wounded and a battalion needing rescue and stuff like that. So I'm just writing that in blog now. The only difference is that the probability of a soldier being wounded, I'm making the model more detailed now, and I'm saying that it depends on whether the soldier is experienced or not. There's the probability of them being wounded is different. But basically that's the same example as before. So if I have a blog like that, a blog model like that, and I want to know what is the probability that a battalion needs rescue. So how does the inference work? It's sampling, right? So when I have this query, I need to know what its distribution. So that's going to depend on its parents. And its parents, as we see here, you have this, it's an existentially quantified sentence. So that's going to depend on all the soldiers. I have to look at all the soldiers, the set of soldiers, and see which ones are in the battalion and how many of them are wounded. So that's one of the parents of my variable here, is the set of soldiers for that battalion. So I sample values for that. And once I have a set of soldiers, I have the parents of this variable that I need, which is going to be the variables wounded for each of the soldiers. Once I do that, I have to sample, okay, is the soldier wounded? Now I need to sample a value for that. I need to determine its distribution. I need to know which, I have to have values for its parents. So the parent there is whether the battalion has been attacked. So if I do that, I can sample a value. If I get false, it means the battalion is not attacked, so the soldier is not wounded. And unfortunately, I'm going to do the same thing for all the variables, right? Even though I know that the battalion is already attacked, I should be able to tell that all the soldiers are not wounded because the battalion is not attacked. But I'm going to sample values for each of them, and it's going to be false for all of them because that's the distribution. And because of that, whether the battalion needs rescue or not is false. So that's how it works. Just another example. Yeah.
Something sort of interesting there. The notion that the battalion has members, i.e. the soldiers, and then if this attacked thing holds for the battalion, it holds for each of the members.
Mm-hmm.
Right? You needed to know that it wasn't an individual soldier that was attacked, but that the battalion was attacked, and therefore each of its members was attacked.
think you have to interpret it.
I think when you write this statement there, let's see. So here, right? If a battalion. So I have this variable that says to which battalion a soldier belongs to. That's something I didn't go through over in very much detail, but when I have a number statement for soldiers, I'm saying for each battalion I have a number of soldiers, and that actually constitutes a function on soldiers. So I have this function called battalion of that's going to give me the battalion to which the soldier belongs. So if I do that, I have, if the battalion to which the soldier belongs is attacked, then I have a, right? Does that make sense? I don't know if that answers your question.
Yeah, so if you go back to that picture,
Yeah.
the way you were explaining it, you were sort of going through variable by variable and saying, okay, what parents do I need to know about in order to figure out if this variable is true? And you got to wounded soldier 1 and you said, oh, I need to know about attacked. And then when you got to the next wounded soldier, you knew that that was going to depend on that same
variable. Yeah.
Presumably in other cases it would depend on a variable that's not the same.
Yes.
So there was this membership concept. Are there any other concepts that we should know about that come in handy when you're deciding what depends on what?
Well, I don't see those are separate cases, because what I do is always the same thing. I look at the statement, the dependency statement for this, and it's saying, well, look at the battalion of this soldier, and that's going to be your parent. So it determines that, okay, I need to know this variable. This guy is going to do the same thing, and it's going to, just because that's how that computation works, it's going to get exactly the same variable, then it's going to look up there.
So the language allows for these functions like battalion of, which are sort of arbitrary, and you can define
Yeah.
them as you wish, and then you're just sort of chaining them.
Well, they're not arbitrary exactly because
How expressive they get.
this function battalion of is what we call an origin function. It's actually, it has a very, it's not even a probabilistic variable, because when I need to know the number of soldiers in a battalion, right, I have to sample that. Okay, I need to know how many soldiers this particular battalion has. I sample a number. In that case, it was 73. When I do that, I generate 73 objects that I place on my universe. And then I define the origin function for each of them to be that battalion that generated them. And that's a fixed value for all of them. So when I go to wounded dependency model, I say, well, is the soldier wounded? Then I plug the soldier here, then battalion of is already determined because that was determined when the soldiers were generated. So I have a value here, battalion 13. So now I know that I need to know whether battalion 13 has been attacked or not. And then I sample that.
So you have this sort of generation story, right? Like the
Yeah.
battalion sort of has over the soldiers.
Yeah, it's a very much generative model.
How would, like, for instance, would you be able to model like a set of battalions with a set of soldiers where different like a single soldier can belong to 2 battalions, like, you know, can be journeyed from 2 places, or like, you know, or does that get to like beyond?
No, you can do that. You can do that, but those wouldn't be origin functions, because the origin function is defined as a parameter of the number here, right? Once you have that, you're saying all the soldiers are coming from the same battalion, so that's it. But you know, you can define arbitrary functions on things. I could also have another variable here, say alternative battalion of, and then it could be anything.
Right.
Yeah, and then I could use that variable if the battalion has been attacked or the alternative battalion has been attacked. So even though those origin functions, they are under the hood different, they are treated, you can use them in the same way as any other function. So it becomes a very uniform process. So do you see now that it's actually always the same case, that you're always looking at the parents like that? I'm asking that like the other.
Sort of. I mean, well, I guess what I'm getting at is like if you, this is like a programming language. And if you define a programming language, you know, you say, okay, I have base types, I have integer, I have characters, I have real numbers, I have basic atomic functions, I can add, I can subtract, I can multiply. And I'm trying to get at that's what exactly is this set of basic operations that you could define here and basic
Yeah.
types of types and so forth. Like if you do define it as a programming language, what's a set of things?
You have the built-in types like natural numbers and Boolean and things like that. You also have user-defined types like soldier and battalion. And then you have these operations, right? Here I'm not showing many of them, but you have things like plus and minus and all that. And it always works the same way. You execute these instructions here. Every time you need the value of a variable, you look to see if it's already defined and already has a value. Or if it's not, then you sample a new value for it. And when you sample a new value for it, you're going to trigger this recursive process in which you sample that variable's parents and so on. So eventually you sample them, and then you have this partial world representation. So it's always just this loop. Sample parents, get distribution, sample value for variable. And if you get evidence, that's the same thing too. You get the evidence and you need to know to sample parents of the evidence and see if that's a likely explanation and so on. So this is one example, right, in which I had to sample values for all of the wounded variables. I can have another one. Suppose that the battalion has been attacked now, that I'm sample things, and in this particular sampling run, the battalion has been attacked. And now it's a different sampling run, so I actually have a different number of soldiers. In this other world here that I'm generating now, that battalion has 49 soldiers. So the battalion has been attacked. So now, and that's an interesting thing in BLOG, right? It uses this context-dependent independence here, which is context-specific independence, which is now that I know that the battalion is attacked, now this variable matters. To know the distribution of wounded, I actually need to know whether the soldier is experienced or not. So if I go through the dependence model here, okay, it's been attacked. So now what's the experience of the soldier? And then I'm going to sample something here. Once I do that, then I have a distribution for wounded. Suppose it's true. And if it's true, actually you have, just like in regular programming languages, right? If you have a disjunction and you get a true, then you know that the result is true. You don't even need to look at the other one. So in this particular case, we take advantage of that, and the other soldiers, you don't actually have to do any sampling because you already answered your query. So. But you have to run this many times, and many times it's going to be that you have to sample all the soldiers. So BLOG has this lazy evaluation property, which is nice because as opposed to some other methods, right, in which you propositionalize first and then you start doing the inference, BLOG is doing the inference and propositionalizing as it goes. And as a result of that, it saves work sometimes. So DBLOG. DBLOG is just dynamic BLOG, just like you have dynamic Bayesian networks. So it's trying to use BLOG for temporal models. Now, because BLOG is so expressive already, you don't really need more expressivity to express temporal models. You can just use natural numbers as time steps, and you just write your statements that depend on the previous time step, and you're done. So that's a legitimate question. Why do you even need to bother about dynamic BLOG? You could just write a BLOG model that has time. And the reason for that is that temporal problems have a lot of structure that you want to take advantage of. So you have this Markov property there. If the algorithm knows that that's happening, it can take advantage of that. Also, usually in these problems, you get the evidence and query successively 4 time steps. So usually you know that once you are in a new time step, you're never going to get evidence about previous time steps. And you may want to take advantage of that. So the language remains the same, but it's still nice to use a different algorithm that takes advantage and is more efficient for temporal models. So we're working on dynamic BLOG. We do make this change to the language that if you just use natural numbers, the algorithm doesn't know whether that natural number is actually representing time or not, right? Because it could be just some natural number. So what we do have this new type, it's time step, which is just natural numbers, but it's actually telling you this is representing temporal structure. So the algorithm knows. But it works exactly in the same way. You just have different literals. Now instead of 0, you have @0, things like that. But it works exactly the same, so much so that if you give this to the blog inference algorithm, it still deals with that, because time step is it's just one of the built-in types. But it's not going to take advantage of the structure. So we have DBLOG particle filtering, right? So particle filtering, as most of you know, it just works by, you have some samples for state for a particular time step, and then you get new evidence, use likelihood weighting, and you see how likely an explanation each of them is. Then you resample to get population that represents more likely hypothesis. And we do the same thing in DBLOG. So you have a world there, you have this partially instantiated Bayesian network for a specific, that represents a particular explanation that you sampled. And then, oh wait a second, this slide is still about dynamic Bayesian network, so that's not about BLOG. But it's essentially the same thing. You just sample the new variables using the time slice, and you generate a new particle. So for DBLOG, you have this particles. The particles now represent what I was showing before, that network of variables that require the instantiation of each other and so on to generate an explanation for your query or your evidence. So when you get new evidence, and the evidence is going to be BLOG statements like that, then you need to explain it. So here what I'm saying is that, well, I didn't actually explain this model, so let me go back really quick. This is about aircraft. I have a bunch of aircrafts. They have their positions at each time step. That's going to be a random walk depending on the previous position. And I have blips that this aircraft generating in a radar. It can be one blip, or maybe it's not detected in that particular time step, right? The number of blips is going to depend on the aircraft and on the time step. So each time step, I may or may not generate a blip from an aircraft. I can also have another set of blips that are just false alarms. I can have some noise blips. And those blips are going to have the apparent position of an aircraft. That's going to be a Gaussian noise around the position of its source. So here, source is another one of those origin functions, right? That's going to be the aircraft that generated the blip. So I just look it up here. What's the position of my source? Well, actually that shouldn't be previous time step, should be the current time step. What's the position of my source at this time step? And then there's a Gaussian noise, and that's the position of the blip. So that's the model I'm using here. So if I have the situation, I'm saying, I'm observing now that the number of, that I have one blip only that comes from this aircraft, that I have exactly one. So it has been generated. And the apparent position of this blip is 3.2. So I need to get a distribution for this variable, apparent position of blip B1 at time 2. Because, yeah, I was using time step 2. So I do that by sampling a value for B1, which in the case here, that's not a very interesting example, because B1 is always going to be the blip. There's only one blip generated anyway. It's not a set of blips per aircraft. So that's going to be a very simple thing. I'm just going to instantiate B1 with the blip that the aircraft generates. And if the aircraft doesn't generate a blip in that time step, it means this particle will have weight 0. Then once I know that, I need to know also what's the position of the source. So I sample now the position of aircraft 1, and that's going to depend on the position on the previous time step. So I use the previous particle as a set of already instantiated variables. And then I explain my evidence, and then I have a weight to evaluate this particle that I just generated. And like before, I have this lazy instantiation. I just instantiate the things that I really need in order to explain my evidence. So now we have an issue that doesn't arise in dynamic Bayesian networks. Because you could think, well, dynamic blog is just like dynamic Bayesian networks. There's nothing new. But you start having some issues that you don't have before. This lazy instantiation is one of them. So just like in that particular case, but now for time step 8, time step 9. If I get a new blip, and this time it comes from aircraft 2. And suppose that I haven't observed aircraft 2 since the beginning. It's the first blip that comes out of aircraft 2. I'm going to have to sample the position of aircraft 2 at time step 9. But because I have lazy evaluation, instantiation, I'm not going to have any values for that in the previous time step or the previous. I'm going to have to go all the way to the beginning. So the cost of this lazy instantiation of variables is that you may have to do something like that. And so the nice property of dynamic Bayesian nets, where you have a constant update time, would go away in this case.
Are you guaranteed that somehow that doesn't affect the particle filtering that it shouldn't? That you would get the same answer if you had just instantiated those right from the beginning?
Yeah, you're wondering that what I did before didn't depend on position of aircraft 2, right? It doesn't, because the fact that it has not been sampled means it was irrelevant to the evidence. So even if I had instantiated it, the evidence would have exactly the same weight. So yes, it is guaranteed that it doesn't matter. It only matters in terms of cost.
In a real-world system that at scale, we can imagine an adversarial attack on the system to really bring it down by hiding, obfuscating future aircraft and then revealing them in certain ways that would sort of become intractable.
Right. So you could think of something like that. And you know, it sounds like this is a problem.
So if it doesn't affect the probability of the previous time step, why do you need to run Joey extension?
Well, because now you got evidence that depends on it. Like up to now, you never had to bother about it. No matter where you were, the evidence would have the same weight. But now, because I'm saying that this blip comes from aircraft 2, and I'm telling the position is here, I need to...
I mean, you can instantiate for this concept.
Yeah.
And you don't need to go back.
But to instantiate this, to sample a value for that, I need to get its distribution. And its distribution depends on the previous time step. And it's a recursive thing.
Closed form solution, right? At least if it's a random walk, right? You know it's been
Exactly.
200 steps. You don't have to actually do it.
Right. So, and actually, you know, this is a very common problem in AI, data association. People have worked on that, not with blog, but, you know, just handmade systems. And they have circumvented this problem. They don't generate things all the way to the back, basically using things like closed form. And that's an option that's available to us as well, because we know that this is a random walk. We could also code the model in such a way that's bringing that closed form there. Just like previous work, people had to sit down and think, hey, what's the closed form of this? And then they worked it out in their system. We can do the same thing here. But it's something that's not done automatically. You have to think about it and write it down. This actually... I don't know as much about dynamic Bayesian networks, but I would assume that people may have worked with lazy instantiation dynamic Bayesian nets too, right? And then they would run in the same problem as well. Do you know of anything like that? Because that's not a blog specific thing. If you have a dynamic Bayesian networks with lots of variables and many of them are not relevant and you don't want to instantiate all of them, then again it would run into the same problem. Yeah.
To do that sampling, so if position A2 at time 2 depends on any of the state for the particle at time 2, then would that mean that you wouldn't be able to just closed form figure out what it would be at time 9? You would actually have to go through the sampling, or can you?
No, I could look at the particular distribution there, the transition distribution, and maybe I could figure out some closed form. Right? Is that what you're talking about?
Right, yeah, I guess I'm wondering if, if the position only depends on the start state and then how much time it's been, then you can definitely do the closed form. But if it depends on, for each particle, some of the other state factors that had been sampled in that particle, then it seems like you can't do a closed form. You'd actually have to keep the history of the particle so that you can go back in time.
Because maybe the history of the particle affects
like if position of A1 affects position of A2, then you need to know A1 at time 2.
Yeah, so the closed form approach depends also on whether these objects are interacting among themselves. Yeah, so
it would depend on the evidence. So if evidence change, so at least your closed form has to take the evidence as input.
Well,
the evidence for the previous timestamp.
So what do you do and what people have done in data association models in the past? When you get an observation of something that you don't believe has been observed before, then you use the closed form. Because I never got evidence about this guy, so I know that's the distribution of this time step, given that I got no evidence so far. Now, if you have observed it before, then you have to use the history, right? Because you actually know something about that object. So you may have another closed form, but that somehow depends on the history. So so you have to do that.
Right now you're assuming that you deterministically know which aircraft is giving you which bleed. When if you sort of put
right, that's not the usual situation.
So if you put an uncertainty over there, then you also have to infer about whether the bleed came from aircraft 1 or 2.
Yeah.
In that case, closed form won't do anything.
Yeah, you're absolutely right. When you don't have, if I just tell you, hey, that's my set of blips, that's their positions, I don't know where they're coming from, then you have to generate the positions of our aircraft to be able to explain that set of blips. And then this problem of retro-instantiation wouldn't occur because you're always instantiating everything. So you always have everything available.
But if I'm only getting one bleep at a time.
Even that, right? Because I say, well, okay, where's this blip coming from? I have to instantiate all aircraft and see what's more likely which aircraft is more likely to have generated it. So then that problem would arise, which is not necessarily a good thing because it would be instantiating everything. And again, you could have a form of lifted inference, right, in which you keep closed form representation for a generic object representing all objects that have not been observed so far. Because those are indistinguishable. You know exactly the same thing about them. You know the prior at the beginning, and you know that you never knew anything else. So you could use some kind of listed inference. And actually, when you look back, previous work in data association, essentially that's what people are doing. They are implicitly representing the unobserved objects with a closed form thing without representing individuals. So, but that's all done by hand, and it's done for specific models. The challenge here is actually having an algorithm that can take a model and figure all this stuff out. Closed forms and lifted inference and all that. So it's a...
So I wonder how this interacts with the open universe assumption. So suppose if you, at the beginning, you only generate a number of how many aircraft you have. Suppose you sample to be 1. And later on, you actually have evidence of 100 aircraft. So how do you reconcile?
Yeah, so that's a good point. This is a temporal. The number of aircraft here is an atemporal variable, right? That once you sample it, it's done. It's fixed. And that's a problem that arises in DBNs as well. Because if you have DBNs with atemporal variables, you have to do something smarter than just sampling it once. And people have come up with solutions for that. One of the solutions is to, at every time step, to apply a transition kernel that preserves the posterior, and that changes also the variables of the atemporal variables. We could do that here as well. We could change the number of aircraft at some point. But then you're going to have to regenerate the history. It's going to be a very expensive...
So how do you handle that?
We don't handle that right now, actually. That's still something to be dealt with. We are working on having a MC transition kernel that we can apply to blog models, which is not that simple. Once we do that, then we can apply to a temporal models, but then we still have to figure if it's going to be, how efficient it's going to be to change those variable values. It's still not very clear to us.
Is there no hope for dynamic programming approaches? Is that just not applicable?
I'm not sure, because the structure here is so, dynamic programming usually depends a lot on, exactly your variables and everything is fixed, But we haven't thought that much about that, so maybe there is hope. So some of the things that we can mention about retroinstantiation is that one possible way of dealing with it is pre-instantiating things that will eventually become necessary, even if they're not necessary for the current evidence. If you know the type of queries and evidence that you're getting, a template kind of queries and evidence, then you can infer what variables need to be instantiated. You could even do smarter things like what's the probability of needing this variable and instantiating it according to that probability. So you can do pretty sophisticated things here. Another thing is using things like mixing time to decide how much to sample back. Maybe the initial position is completely irrelevant at this point anyway. So you can also try to make a decision how much to sample back. And the closed form things and the other things that you mentioned are also ways of dealing with it. Okay, last issue on blog inference that's not related to retroinstantiation or even to DBLOG. DBLOG, turns out that as we worked with DBLOG, we found many limitations in blog. Because this data association, for example, was one thing that brought many challenging things that we had to rethink about blog. So this is one of those items. So just showing here how basic things work, right? Rejection sampling. You get the evidence, then you sample the value for that evidence, and you see if it's equal or not, and then you keep the sample if you get the evidence. Then you have likelihood weighting. You have the evidence, you sample values to know its distribution, and you weight the sample according to the likelihood. Now suppose you get evidence like that. I'm telling you the set of values for happy P for each person P is true, false. So how do I do likelihood weighting here? I could sample the values of those variables, right? Suppose I know I have 3 people, and then I sample that, and I get true, false, false, and that doesn't match the evidence, so I throw the sample away and I keep doing it. In this particular example, it doesn't look so bad because it's only 8 possible values, but it's still pretty bad. Now, if you have variables with lots of values, then it's going to be pretty hopeless. And if you have continuous variables, then it's really hopeless, right? You're always going to get probability 0. If you just sample the values and then you compare with the evidence. This becomes just like rejection sampling. It's no better than rejection sampling because you're just sampling the values and comparing to the evidence. Even though, technically speaking, this is likelihood weighting. It's not rejection sampling because the evidence is this variable here, and we are not sampling that. But because you have a deterministic function between the evidence and its parents, ends up being just as bad as rejection sampling. So this is one of the problems that we came up. This is very much like, this is the bleep situation, right? If I tell you that's the type of query that's going to be more common in the real application. I just tell you, okay, I'm seeing 3 bleeps and those are the positions of the bleeps. I don't know where they're coming from and so on. So you have to give the likelihood of such evidence. And if you just sample those variables, it's not going to work. And this was not supposed to be here. So here what we do is the following. Instead of just doing blindly likelihood weighting, in which you sample values for the parents and you compute the likelihood, here what do we do? When we sample the value for the parents, we determine its likelihood, and we know here its distribution. We know it's a Gaussian. So now I know that to have a valid sample, I need to have one of those values. So I just do an importance proposal that's going to pick one of those values proportionally to the likelihood of each of them. So if I do that, here I pick, for example, 1.2 for that parent. And then the probability of picking 1.2 is going to be proportional to the likelihood of each value. So I know the probability of getting that value in my specific proposal. I can keep track of that. And then I do the same thing for the second parent. Now I only have two values available. I have this choice. I keep track of that choice likelihood, probability. And then the last one, I don't even have a choice. So now I have a proposal distribution that's going to be much more efficient. It's going to work. And not only that, it's going to pick values not only that are valid, but also that are usually more likely. Because I'm going to consider the distribution of the parent before I pick the value. So this is one of the changes that we did. This is not even DBLOG. This is just blog. This is just the blog mechanism for giving likelihood to evidence. And the nice thing about that, the important sampling part of it, it's very well known. It's something that people do on a regular basis, but usually people do this by hand. And the nice thing about having this language that has high-level constructs like sets and so on is that the model automatically can look at this construct and build a proposal that's going to be effective without you having to say anything. This is something, I don't have to write a proposer to get this done. I just write my evidence and the algorithm looks at it and sees that this is a set and that's how I have to do it. So that's one of the advantages of having this higher level structure available to the algorithm. All right, future directions and all that. One of the things I mentioned to you before is that lifted inference is an exact procedure that requires clusters of random variables to be symmetric, and that's not a very realistic assumption. So really we have to do something that uses approximations. The intuitive example here is the following. If I'm thinking about the population of the United States and I'm trying to make decisions, estimate probabilities like in the elections and things like that, I don't have to consider every individual. Even though each individual, I may have particular facts about each of them. I may have databases talking about all these people, but I still can do some kind of lifted inference if I'm willing to ignore irrelevant factors or things that are somewhat relevant but not much, or that not going to affect the result all that much, so I can ignore that and have something that has a margin of accuracy. So there is a generalization to lifted inference that takes that into account, that doesn't require symmetric objects. So that's a very important direction. Another thing is parameterized queries, right? What I showed before, the queries always were propositions. And the reason for that is that if you have unbound variables in the queries, then you have to keep track of possible values for the logical variables in the queries, and it complicates things. But it would be really interesting to be able to ask something, what's the probability of X being sick of measles? And then the answer is something like this. If X is John, then the probability is such. If X is Mary, the probability is such. If X is someone else, any of the other people, the probability is such. Also, it would be a nice link to logic programming, because that's what logic programming does, right? It instantiates, it binds all those logical variables for you when you give a query. So that's something that's still to be done. Also, we don't have function symbols explicitly, so that's also nice if we could write things like that. As I was saying before, right, the lifted inference language is not very expressive like BLOG is. So these are all directions to make it more expressive. Also using equality, adapting paramodulation, things like that. And of course learning the parameters of functions. And okay, the take-home messages here are the following. So it's useful to keep the first-order representation not only for representing your model, but also during inference and using that in the inference. If you do lifted inference, then you have something that's equivalent. It gives you exactly the same answer as the grounded inference, but it's much faster. Oops. And as for DBLOG, this is about bringing these techniques, temporal processing, to this first-order representations and all the variations that requires. So basically, what I want to do in the future is, to increase the lifted inference part of it and come up with something that's an inference engine that people can actually start using for real problems, and not very different from what Pedro Dominguez is doing with Markov logic networks. He has already a pretty advanced engine, and that's the direction that I also want to follow. Although he's using very different techniques now. So now he started using lifted inference, but before he was also doing propositionalization and so on. And that's it. Thank you very much for your attention, for staying for so much long.